Sorry. No. Okay, good afternoon, everyone. The third seminar this semester. Today we have the pleasure to host Bryn Haskell from Klaus Copernicus Astronomical Center of the Polish Academy of Science in Warsaw. And Bryn did his PhD in Southampton, and then he did a couple of postdocs in Europe. He was in Australia, and he's back in Europe and working as a professor at CAMK. And he will tell us about astrophysics with continuous gravitational waves, and the results are based on the paper that is written on the first slide. The floor is yours.
All right. Thank you very much for the invitation. And you've already said what I'm going to be talking about. So I'd just like to talk a little bit about continuous gravitational waves and review the observations from the third observing run of LIGO-Virgo-KAGRA gravitational wave detectors. And as I've written here, this is based on a review that we wrote with Michał Vega and has recently come out. So you can find it at that link if you're interested. So first of all, if I can switch slide. There. I guess you all know, but very quickly, what are gravitational waves? Well, what we're talking about here are essentially waves, so ripples in space-time itself. And so if you think of a metric, g mu, which we divide in a background piece, which you can think of as just a flat metric, and on top of this, you have a perturbation, which is this h nu here, which is something small, but that oscillates and is essentially due to the movement of very energetic astrophysical bodies. So we're thinking compact objects here because we want something that can really deform the space-time and possibly moving close to the speed of light, because we need this to be really energetic. And so essentially we're thinking in most cases for the first detection, things with black holes and neutron stars. And you know, I said this is something small, and though nevertheless, you know that these events are being detected, they're being observed. And the idea is that you can do this with an interferometer. So essentially, if you have a Michelson interferometer, you have two arms, and you measure the length of these arms very accurately, shooting lasers, they bounce back, you measure the time it took, you have a very accurate measurement. And if a gravitational wave hits your detector in the meantime, what it does is it starts to wiggle these arms around in a way that you can basically see up there. Depending on the polarization of the wave, it'll first squeeze one and stretch the other, or do so in a kind of cross way, pulling and stretching. And so you end up with one arm that gets slightly shorter and one that gets slightly longer. And the amount by which the arms are shortened or lengthened, this delta L, over the length of the arm, is proportional to the amplitude of the wave. Essentially, it's h naught, let's say the modulus of that h that I wrote very roughly. And of course, the effect is very small. We don't usually see tables doing that and stretching and squeezing while we use them. And if we think of energetic astrophysical events, so think of a reasonably nearby supernova or mergers of black holes at distance of a megaparsec or something, the kind of amplitudes we're talking around are order 10 to the minus 21, which means that if I have a 10-kilometer long arm, its length is changing by roughly 10 to the minus 17 meters. So I have a 10-kilometer arm and its length changes by less than the diameter of a proton. So that is the kind of shift that we're actually trying to measure. And as you know, it sounds impossible, but it is actually being done. And there is a network of such interferometers. So there's two LIGO detectors in the United States, Virgo in Italy, KAGRA in Japan. There's LIGO India that's being planned, and there's another detector GEO in Germany that's used mostly to experiment with new technologies. And the first signal was detected in 2015. So this was a binary black hole merger during the first observing run. And in 2017, there was the first observation of binary neutron star merger. And this was in 2002. What I'm going to talk about today are observations during the third observing run, so 2003, that finished a couple of years ago. And currently, the fourth observing run, so 2004, is ongoing as we speak. Okay, so I told you about these mergers that were detected. I want to talk about something different today. So I'm going to talk about 2003 results, but not the compact binary in spirals. There were several of those detected, but I want to talk about a class of signals that was not detected yet. And these are continuous gravitational waves, so long-lived quasi-monochromatic signals. So essentially, if you want the gravitational wave equivalent of a pulsar, and in fact, the sources we think about most of the time are neutron stars, so continuous emission from a deformed star, or in fact, we can think of doing astroseismology, so emission due to modes of oscillation of neutron stars. And, given that we are talking about neutron stars, and this is what I'm really interested in, you'll allow me a brief just digression to talk about why it's interesting to search for signals from neutron stars. And this is because from a theoretical point of view, they really allow to probe aspects of the fundamental interactions that we can't study otherwise. So if we think of the QCD phase diagram, so you have temperature versus density here. We kind of know what happens at low densities and temperatures from terrestrial experiments, and we can do theory along the temperature axis. And also at asymptotically high density, one perturbative QCD sort of tells us how deconfined quarks are going to act. But at intermediate densities, things are more complicated. We can study quark-gluon plasmas with heavy ion colliders. But again, here, we're looking at very energetic events where you're colliding these particles. So we are always looking at the higher temperature regime. So at these high but intermediate densities and low temperatures, really neutron stars are the only way to understand how fundamental interactions behave. And so, another way of looking at this is looking at what the equation of state of dense matter is. So we want the relation between pressure and density. This plot, you see the low densities, we kind of know what this looks like from nuclear physics. At very high densities, we have theoretical predictions, and in between is where we try to understand it with observations of neutron stars. And to date, these were mainly observations from radio, so measurements of masses of pulsars in binaries. So if you measure a mass, you know that your equation of state has to allow you to build a neutron star that has at least that mass, otherwise it can be excluded. There are some constraints also on radii from X-ray observations, and recently also constraints from gravitational wave detections, so from constraints on the tidal deformability of the neutron star. And these came from this observation, I'll mention it very briefly, of the first binary neutron star in spiral, so GW 170817. So this was a very interesting event because it was really a multi-messenger observation that there was first a detection in gravitational waves of the in-spiral, then the associated short gamma ray burst was detected, followed by the kilonova emission, so the emission from the ejector expanding and cooling down. So this allowed for a lot of constraints and also to get a handle on the tidal deformability of the neutron star, so the amount by which it gets squashed by the tidal field of the other neutron star. So really, we can start probing this high density interior with electromagnetic observations, gravitational waves, but now the neutron star in spirals. In the future, maybe also we may be able to detect neutrinos from some of these in spirals. But what I want to tell you about today is a way to add other messengers here in the gravitational wave part of this plot, and so add these continuous signals that can tell us more about the composition of the interior of the star. So how do we think neutron stars can emit continuous gravitational waves? Well, essentially, there's two main mechanisms that we think of. One is what we like to call the mountains. So what these mountains on neutron stars are non-axis symmetric static deformations of the neutron star. So we say mountain, but we really want something global deformation. And then if it's on the neutron star is rotating, this gets swept around by rotation, and so it couples to the gravitational field and sends out gravitational waves. And you have emission at twice the rotation frequency in general. These are quadrupolar deformations to leading order, but depending if the symmetry axis is not the same as the rotation axis of the star and it's inclined, you can also have emission at the rotation frequency of the neutron star. And we usually quantify this in terms of an ellipticity, and you'll see some of these later. So that's the proper definition in terms of the moment of inertia tensor. But if you want to understand roughly what it means, you can think of this as taking the difference between the semi-major axis, so that B and A there, if the star is triaxially deformed, and then normalize it by the z-axis. And so that tells you how deformed the neutron star is. And of course, another possibility, the other main thing we're looking at are modes of oscillation. So if you have oscillations in the star and stuff sloshing around inside, this will also couple to the gravitational field and give you gravitational waves. And see, the main candidates here that we look for are the fundamental mode of oscillation, the F mode, and also the so-called R mode, which is a toroidal mode of oscillation, for which the restoring force is a Coriolis force. And that's what you see here. And you'll see later that this is interesting because it's at an interesting range of frequencies for detection, and we think that these modes could actually be excited in some neutron stars. Okay, so what happens here? So we have maybe a mountain or neutron star, it's going around, and so it's emitting gravitational waves continuously. And these signals, we think, are intrinsically fairly weak, so significantly weaker than the mergers that we have detected. And in fact, it makes sense that those are the signals that were detected first. But the advantage here is that if it's on all the time, then as your observation time gets longer, you can try and build up signal to noise and dig the signal out of the noise. And this is where the searches become difficult. It becomes computationally quite complicated because if you have, say, a stretch of a year of data, now you have to take all this data and start doing Fourier transforms at every point of the sky as you're searching for different parameters for your signal. And this becomes rapidly impossible from a computational point of view. And so you have to start thinking of dividing the data into smaller chunks that you can analyze coherently and then add up incoherently. Of course, the shorter it gets, the worse your sensitivity, because you can't build up signal to noise ratio. And this is where actually electromagnetic observations come in and can help you, because if you have an idea of which neutron stars that are observed electromagnetically could be a good target for your searches, then you can use the information that you have from electromagnetic observations and feed it into your search. So you can do a targeted search where now you have, you know the sky position, maybe the frequency derivative, so you don't have to search over many parameters, and so you can do a much deeper search. Then you have, of course, every time you know less about the source, there's a trade-off in sensitivity, so you can have narrow-banded searches if you're not sure what the frequency of the signal should be. Directed searches, maybe just the sky position but not the frequency. And then, of course, the most computationally expensive and less sensitive are completely blind searches, where you just do an all-sky search for signals from sources that you just know nothing about. Of course, these are less sensitive, but there is an advantage here that you remain sensitive to things that you just didn't know were there in the first place. And there is an expectation that this might be possible. Very simple argument is just that if you look at the supernova rate, the neutron stars that we have in our galaxy should be sort of order 100, roughly more than the ones that we actually see. And so even allowing for observational bias in detecting these electromagnetically, there still is the possibility that some of them are not seen electromagnetically, but are gravitationally bright, just spinning down due to mainly to the emission of gravitational waves. And a blind search could, of course, find this kind of source. Okay, so to get an idea of these ellipticities, the kind of numbers that you have to keep in mind when I'll show you the results later, there's one main benchmark that we can use, which is the spin down upper limit. So I told you now, talking about neutron stars spinning down due to gravitational waves. And in fact, for known neutron stars, for the ones that we do see electromagnetically, we can derive an upper limit just by observing them, seeing their spin down rate measured, say, in radio, and then looking what the gravitational wave amplitude should be if that spin down was entirely due to gravitational waves. Of course, this is an upper limit because we know that's not the only way they're spinning down. I mean, we see them in radio, but it gives you a handle. So your sensitivity of your instrument has to be better than this limit to actually start making physical sense in the constraints that you're putting. Then you can go to theory and try to say, well, how large do we think these mountains should be? And you can do various calculations. So let's say for standard equations of state, hadronic equations of state, you think that you can have a mountain that's supported mainly by elasticity in the crust. So similar to what happens on Earth. The material is a bit different, of course, and we think here that you can have this ellipticity in epsilon of around 10 to the minus 6 before you break the crust. So for a 10-kilometer neutron star, this would mean a mountain that's roughly 1 centimeter high, to put it in perspective. But still, of course, there's a big change in the impact on the gravitational potential around that. You could have even larger deformations if it's not the crust of the neutron star that's holding it up, but rather the core. So if you have something more exotic, you could have deconfined quarks. Some of these could be in some kind of crystalline state. And in this case, you could have deformations of up 10 to the minus 4. Nevertheless, for these kind of numbers, really, I'll show you, we still are sensitive, and you'll see it, to signals from neutron stars in our galaxy. So this should be clear. Okay, so are there sources, are there neutron stars in our galaxy that could be interesting to look at and try and target for gravitational wave searches? And there are a few that have been suggested. So I'll start with older neutron stars. So one of the first targets that were suggested are actually very old neutron stars that are in binaries and are being recycled to rapid rotation by accretion. So thinking of low mass X-ray binaries where you have a central neutron star that's accreting from a less evolved companion, so it accretes matter via a disk and it gets spun up. And the argument here goes, is born from the idea that, well, if this is possible, you'd think that you'd be able to spin up the neutron star until it's spinning fast enough that it reaches its Keplerian breakup frequency. And that depends on the equation of state, but in general is well above 1 kilohertz. We did this at some point, and on just very general considerations of causality and what we know of low density physics in the outer layers of the neutron star, this should be at least 1200 hertz, and many microphysical equations of state predict higher breakup frequencies. When in fact we do not observe any neutron stars spinning above 1000 hertz, and the fastest is 716 hertz. And if you look at the distribution, there is a little bit of a pileup as we get there. And so why is this? Well, of course, there's a lot that we don't completely understand about the accretion process itself that could explain this. Could just have to do with selection bias with the donors that are involved. There are many unknowns in this problem still. But one of the suggestions that is interesting is that actually what could be happening here is that as you accrete, you have a messy process, you start building asymmetries on the star. So you build one of these mountains, and then as it spins up, the gravitational wave torque kicks in and eventually balances the spin up torque due to accretion and sets spin equilibrium for these systems around 700 hertz. And you can look at the kind of size of the mountain that you would need to do this. Obviously, it depends on the system, but it's in the region of an epsilon of 10 to the minus 7. So well within the theoretical limits that we discussed before. So other ways you can make these mountains, well, in general, these could be due to compositional and heating asymmetries during the accretion process itself, and then kept in place by the crust. They could be due to magnetic deformations. So we had a look at this problem also with Neha Singh and Tomek Bulik here. We did some models. We found that you need rather strong magnetic fields, but in fact, in some of these systems, you think the accretion could bury the magnetic field, and there's maybe some evidence for this in the systems that are actually produced via accretion. So the millisecond radio pulsars that we think are what's left over after they've been spun up, the neutron star has been spun up in an accreting system. And here, if you look at where they sit in the PP dot diagram, so if you're not used to looking at radio pulsars in a plane defined by period derivative versus period of the pulsar, and you look at their evolution in the sort of bottom left corner, so low p dots and low period, so very rapidly rotating neutron stars, then this is actually better fit, rather than thinking of magnetic fields, in terms of these stars being spun down by gravitational waves and having some small residual ellipticity of the order of 10 to the minus 9, which in fact is what you could expect if you have now an old cold star that is superconducting in the interior and a standard 10 to the 12 Gauss magnetic field that's been buried by accretion in the interior. And if this is the case, you have this kind of field, then in younger neutron stars, so in the general neutron star population, say something like the Crab, you could expect deformations of up to 10 to the minus 6 as the magnetic field evolves, mainly due to the Hall effect in the crust. So these are the kind of numbers that you may expect from theory in these systems. So how do they actually compare to what we've been searching for in the third observing run? So I'll start by talking about all-sky searches for unknown sources. Of course, as I said, no signal was detected. So what I'm showing here are upper limits. So when you don't detect the signal, of course, you can set an upper limit, and you know that above this threshold, you would have detected a signal if it was there. And so, you know, let's look, for example, the plot on the right. You see you have ellipticity and different lines that correspond to different distances. So you see that for these models, that more realistic ones that involve rather small ellipticity, we're really probing nearby. So we're looking at neutron stars at maybe tens or hundreds of parsecs. If we look, you know, at 10 kiloparsecs, say, so the bulk of the galactic population of neutron stars, and frequencies in the range of several hundreds of hertz, as we would expect emission from most of the known rapidly rotating neutron stars, then we are probing elliptices in a range of maybe 10 to the minus 5. So really here we're, for the bulk of the neutron star population, we're probing these more exotic scenarios with very large deformations. So we are trying to push, obviously, the sensitivity down. And so we hope that the next observing runs will give us more sensitivity and start probing even more of these models. And the situation is somewhat similar if we look at searches for known neutron stars. So in this case, as I said, we can take information from electromagnetic observations. And so what I'm showing in the plots here are these blue. Let's look at the plot on the right again, which is a similar one to the previous one. So we compare the same thing. So ellipticity versus frequency. And in blue, you have the upper limits from the searches, because again, there was no detection. And then the upside down gray triangles, these are the spin down upper limits that I was talking about before. So this is the, you know, the amplitude that you would have if the neutron star was being spun down only by gravitational waves. And you see at lower frequencies, those ones with the green line are the ones in which the search actually beat the spin down limit. So the upper limit obtained from the search is lower. And so for those systems, we're actually constraining the amount of energy that's emitted in gravitational waves. You see, however, that for these systems here, we are still probing elliptices larger than 10 to the minus 5. So we're constraining the energy emitted. We're still not quite at the point of the more realistic predictions of models. And then at higher frequencies, the spin down upper limit is still a little lower. So again, there is some improvement of sensitivity needed before we're probing really these predictions. And one can also look at do targeted searches. For example, one can search for supernova. So in this case, we know where this is in the sky. We don't know what the frequency of the neutron star, if any, would be. Again, here, one can obtain an upper limit looking at the age of the supernova and making a similar assumption. So saying, well, let's assume that it was spun down from birth only by gravitational waves. We have to do better than that upper limit again. And some of these sources, in fact, the searches are, again, below this upper limit. So they're probing physically significant parameter space. And again, move on to the older sources I was talking about before, so the neutron stars in low mass X-ray binaries. And in this case, of course, things are a little more challenging. You have a binary. But again, there are some interesting searches, and an example here is searches for gravitational waves from SCOX-1. So this is the brightest LMXB in the sky. And so it's interesting to look at this just from an energy budget point of view. Of course, it's very energetic, and so we can hope that some of this energy is going away in gravitational waves too. What complicates matters here is that we don't actually see this as an X-ray pulsar. So there's a neutron star in there. We think there is for several reasons, but we don't know its frequency. So the search has to be over a range of frequencies. But still, in the most sensitive range of frequency, the search actually can go below this torque balance limit. And so exclude it in a range of frequency, which of course we can also then translate in some limit on the mass of the neutron star that would be allowed for this if this scenario is taking place. So we're essentially excluding very massive neutron stars, and we can start looking at different equations of state here. This is a very soft and a very stiff equation of state. You see, in the stiff case, we are excluding more massive neutron stars, but also for the soft one. And so we start to restrict the parameter space in which there could be a signal due to a rotating neutron star at spin equilibrium, and how massive that neutron star would be. Okay, but as I'm talking about these older systems that are accreting, there's also this other mechanism that I talked about, the R-mode instability that could be at work in these systems. And so just let me explain briefly what would be happening here. So the R-mode, as I said, it's a mode of oscillation for which the restoring force is the Coriolis force. So it exists only in a rotating star. And it's equivalent to Rossby waves in the ocean, or what's the same as in weather systems on Earth. And it's particularly interesting because if you have a large scale R-mode in a neutron star, the emission is at roughly 4/3 the rotation frequency of the star. So if the star is rotating hundreds of hertz, it puts them in a sensitive region of our detectors. And we also think that in some cases, the mode could grow to large amplitude because it can be driven unstable by gravitational wave emission. And the way this works, roughly, if you look at this animation, is that say you have an R-mode, you're up there. So you're on a rotating observer sitting on the star, and the pattern is going that way. So it's counter-rotating. Then, if you go now to an inertial frame, so you look at this from infinity, the mode pattern is now being swept around the other way by rotation, and you look at the gravitational waves that are coming at infinity, they're removing angular momentum, so they're making the angular momentum even more negative up there, and so the mode is growing. This is a very hand-wavy way of seeing it. In fact, the system can find a configuration with lower energy and angular momentum for the full system in which the star is spinning down and the mode has grown to larger amplitude. Of course, this is interesting because it means the mode could grow to large amplitude and we have higher gravitational wave emission. But it happens only as long as the timescale on which gravitational waves can drive the mode to a large amplitude is shorter than the timescale on which viscosity will damp it. And this happens in a window of temperatures and frequencies. We usually illustrate this in terms of this instability curve, where on the x-axis here you have the temperature, and this is the core temperature of the neutron star. So it's higher than the surface temperature. And on the y-axis, this is the rotation rate. It's normalized here, but it's cut off essentially at the Keplerian breakup frequency. And at very high temperatures, bulk viscosity very generally always stabilizes the mode. Lower temperatures, it's shear viscosity, but in this white region in between, the mode can grow unstable. And in these older systems, what we think happens is that the system, the neutron star, was slow and cooling down, but then it gets spun up by accretion and pops up in the instability curve somewhere up there. The mode goes unstable. It heats the star up because of shear due to this unstable mode, spins it down because of gravitational wave emission, and then essentially you would start the cycle again. Of course, I've drawn very big arrows here just for illustration purposes, but how far inside this unstable region the system would go depends on how large the amplitude of the mode can grow before it saturates. This again is fairly unknown. It depends on the nature of the viscosity and coupling to other modes. But in general, what you should remember for following is that if the saturation amplitude is large, you can maybe end up well inside the instability window, but the duty cycle is very short. System maybe spends a few weeks spinning down very rapidly, and then it takes 10 to the 6 or whatever the accretion timescale is to spin back up. So you would have a system that's essentially off all the time. More realistic models for couplings predict smaller amplitudes, which means that the system sits inside this region longer, but with lower emission, and essentially it slides down this instability curve. So again, you wouldn't expect to have systems well inside. And well, you can actually go and look at this prediction and try to populate this instability window with observations of low mass X-ray binaries. So we can take the systems for which we have a good handle on the frequency, because we see them as X-ray pulsars, and where we can try and measure the temperature. So to do this, you have to essentially be able to measure the surface temperature. So when it's in quiescence, take a black body spectrum that you think gives you an idea of what it looks like, and then model what the core temperature should be like. And of course, this is a bit uncertain. This is why you see these rather large error bars on the temperature and essentially nothing on the frequency. There are error bars there. They're just very small compared to the temperature ones. But what you find, we had a look at this with Nathalie Degener and Win Ho, is that you find there's a whole bunch of systems that are sitting right inside that unstable region, where I just told you before there shouldn't be anything, because they either don't spend much time there, and so you certainly wouldn't expect to catch all those while they're spinning down, or they should never make it there because they're staying close to the instability window. So of course, what this is telling you is that in reality, when I was drawing this curve, I didn't put enough physics in the model. So this is what the curve would look like for a plain vanilla neutron star model with just standard equation of state, hadronic core, no exotica, so no hyperons, quarks in the core, no large scale superfluid degrees of freedom, and things like that. So what several groups have been looking at is, how do you fix this problem? And one answer is, of course, to understand what the viscosity looks like in the neutron star better. So we expect that at higher densities, hyperons can appear in neutron stars, and hyperon bulk viscosity can actually become fairly strong at lower temperatures. So that's what you see on the left, and would mean that these systems would actually be stable in this region. You could also have, if you have deconfined quarks in the core, this could also give you stronger bulk viscosity. So this could explain why these systems are actually sitting there. Or you could have strong superfluid neutral friction due to neutron vortices cutting through superconducting flux tubes in the core of these older and colder neutron stars. So there's obviously a lot of work to do here, both theoretical and observational, to understand what's happening at these lower temperatures. So already you can actually learn quite a lot about neutron star interiors from looking at gravitational wave emission due to R modes, even just with X-ray observations without a gravitational wave detection. And then when you look at this instability window, I've been looking at the low temperature region and what's happening there. It remains the case that the higher temperature region in some ways is easier we have a better handle on what's happening on the bulk viscosity for hadronic equations of state at high temperature. And in fact, it's been suggested that the R mode could be relevant not only for old neutron stars, but actually for very young neutron stars. And this instability could be the way that neutron stars are born hot and rapidly rotating and then end up all spinning down in the sort of rather narrow range of periods that are observed in the standard radio pulsar population. The idea being that now, if we look at the right, so very high temperatures, if a neutron star is born somewhere up there, it cools, then it enters the unstable region, it spins down. Exactly which of those curves it would follow depends on the saturation amplitude, but it doesn't matter so much because sort of independently of where it enters, then it has to exit. And because we're close to the minimum, the curve is rather flat there. And then you end up with a rather narrow range of periods. And showed this plot, which is from a paper by Alfred and Schwenzer in 2014. And so they were looking at this, they were trying to quantify the uncertainty in the equation of state. And so if you look at this plot on the right, this was in terms of frequency derivative versus frequency. See, the neutron stars would be born up there, they'd spin down, and then this band that they've drawn is the bottom of the instability curve, allowing for some uncertainty due to the unknown parameters of the equation of state. And in there, they actually pinpoint one system that they say could still be in this uncertainty band, so it could still be at the end of its R mode driven evolution. So this is it's an X-ray pulsar. It's a young pulsar, J0537 minus 6910. And it's interesting that it's there because it's actually the glitchiest pulsar we know. It's the pulsar that has the most of these sudden spin-up events that are known as pulsar glitches observed. It has these jumps in frequency roughly every 100 days. And actually, if you measure how large the jump is, you can predict when the next one will be. So it's really interesting to study the system. And so several groups are looking at it. We looked at this with Niels Andersson and Danai Antonopoulou, who was also here at CAMK some years ago. And we were trying to see what happens far away from glitches and measure the breaking index. So the breaking index is essentially that up there. So if you write the spin down as law as a power law in frequency in omega, then the index would be this n. And it tells you what the spin down mechanism would be. So if it's just electromagnetic waves due to dipole radiation, n should be 3. And you can try and measure it observationally by measuring the second derivative of frequency, and then you can derive it that way. And so we're trying to see what happens far away from the glitch that shakes everything about. And we found that actually it doesn't seem to tend to 3, but it seems to tend asymptotically to 7. And the same was found by studying also nicer data later on. This is interesting because 7 is actually exactly what you would expect for a constant amplitude R mode spinning down the star. So now this makes this a very interesting system to look at with gravitational wave detectors. So there were some searches carried out already in 01 and 02 data, but this wasn't really sensitive enough to get to the kind of amplitude that you would expect to explain the observed spin down. So we did this again in 03 data. And so the results are here. So this band that you see, this orange yellow band, this is the predicted amplitude of the signal if indeed R modes are spinning down this pulsar. It's a band because, of course, we don't know the mass or equation of state of the neutron star, so that gives you this band in amplitude. It's a band also in frequency because I said that the frequency of the R mode is roughly 4/3 the rotation frequency of the star. In reality, if you do this in relativity, the exact frequency depends on the compactness of the neutron star, which of course we don't know. So given a known frequency for the neutron star, again, this gives us a band reasonable compactness. And then the results of our searches are shown here. These are different search methods with different assumptions, but you see that they're all probing well inside this predicted region, in some cases below. And so if we take the most conservative estimate, so we take the highest limit, we can also convert this in a limit on the mass of the neutron star that would be allowed for this scenario to be true. So essentially, what searchers are doing are excluding very massive neutron stars and very stiff equations of state. So we're saying what could still be allowed is that we have a lower mass neutron star, or anyway a softer equation of state, and the neutron star is indeed being spun down by gravitational wave emission due to R modes. So we hope to look at this again. There are nicer observations that are ongoing, and I didn't say, but the multi-messenger approach is essential here because we need information from X-ray timing of this system to know when it has these glitches, because we have to search around them and have to feed this information into the search. And then, hopefully future searches can either exclude this scenario completely, and so then that R modes are not spinning down the system. You have to understand where this n=7 is coming from in terms of interior torques acting on the neutron star. Or if we do get a detection, then you see we would be able to have a very nice constraint on mass, and if you constrain the frequency compactness of the neutron star. So we'll have to wait and see what happens in the future. And okay, that's what I wanted to tell you about searches for neutron stars in O3. But with continuous waves, you can actually look at more than just neutron stars. So very quickly, now that we're reaching the end, tell you a couple of searches that were done actually for dark matter. So you can try and say something about dark matter candidates with continuous wave searches. So the first thing you can do is to search for astrophysical signals, so from gravitational waves due to astrophysical manifestations of dark matter. So one of the things that you can search for are signals from clouds of ultralight bosons around rotating black holes. So here, if you have a curved black hole, just because of the potential, you can have superradiance, you can have this cloud of bosons that builds up around the black hole, and then later it annihilates via gravitational wave emission, and then this signal is a continuous wave signal you can search for. So again, no such signal was detected, but you can put limits now on, for example, the mass of the candidate boson, or formed from such a mechanism. You can also search for signals from planetary mass primordial black holes. This is a binary, but it would be wide enough that essentially you have a continuous signal, so you can use these methods. At the moment, the searches do not significantly constrain the fraction of dark matter that would be given from such kind of planetary mass black holes. But again, this is a method you can use to try and constrain this in the future. And another very interesting thing that you can do if you're searching for dark matter is actually use the instruments of the gravitational wave detectors for direct detection of dark matter. So in this case, what would happen is that if your dark matter candidate is some kind of vector particle, so for example, things like dark photons, and these can actually couple to parts of the instrument itself, whether the photon or other parts, depending on exactly the particle. And then as they pass through the detectors, you get a signal that looks like a continuous wave and can be searched with the same methods that I described here, but it's not actually a gravitational wave. This is a direct detection of these dark matter particles crossing through the instrument. And actually, because these detectors are actually incredibly sensitive at around 100 Hertz, it turns out that at high frequencies, they can actually give you better constraints than other experiments that are currently trying to detect these kind of particles, and so give you better constraint on, for example, the coupling strength for these dark matter candidates. Okay, so that's what I wanted to show you. In all that, the main thing I hope that you took away from this is that, well, on the one side now, gravitational wave astronomy really has started, and compact binary coalescences involving black holes and neutron stars are becoming commonplace, and so there's a lot of physics you can do there. We still don't have a detection of a continuous signal, but I hope I've shown you that in the third observing run, in some cases, we started to reach a sensitivity where we can start looking at astrophysically significant models and parts of parameter space, and start really trying to seriously investigate some of these interesting targets and some of the theories that are out there. And of course, there's a lot more observational work done on the gravitational wave search side, but also obviously we need electromagnetic data to be able to work together. And also there is obviously theoretical work that is needed on the models and to tell us which sources are interesting. Okay, thank you.
Bryn, do we have any questions, comments? Nada, please.
You briefly mentioned supernovas.
Mm-hmm.
So I didn't fully understand. In that case, you want to study check the neutron stars, right, that are left.
Yes.
After. So not at the time of the explosion, but after.
No. So of course there are searches also for the explosion itself. It's a different kind of search because that's more of a burst signal. So it would be very loud, but it's also shorter. So there's a big modeling effort in trying to understand exactly what that signal should look like. No, what we're talking about here is the neutron star that would be left over if then it has some residual deformation, or if it's in fact emitting R modes because it's unstable and so it's being spun down by gravitational waves, then that would be a continuous signal. And so if we think in most cases there's a neutron star hiding inside that supernova, then we know which region of the sky to target, and we can search for different kinds of signals.
Yeah, because I think the way that I understand in general is that currently for explosions of supernovas, the gravitational wave detectors are not sensitive enough, or at least the frequency is not correct, right? So,
well, I mean, there's a lot of uncertainty on what the signal would look like in different phases there. Of course, it depends how far away the supernova is. But yeah, that is a completely different kind of search from the one. So yeah, I'm talking about what's left over after the supernova.
Any more?
So in this R cycle stability, what does it do to cycle of the unstable phase? What fraction of the time is it unstable?
So this really depends on the saturation amplitude, because if the saturation amplitude, as I said, is really large, then it could be something ridiculous like 10 to the minus 6, right? And then you don't expect to see anything in there. If it's smaller, then I can't remember the number now, but it would be on much longer percent of the time.
But you've shown us some constraints, so they assume what to the cycle.
So for the instability, which constraints? Because for these younger sources, the idea is different is that here you are actually in the end. So for the old ones, these are observations. So the idea here is that, you know, these systems should be off. They shouldn't be emitting gravitational waves due to our modes if they are sitting well in the unstable region there. So if I, you know, what I do here is I measure temperature and frequency from X-ray, and then I put it in my instability window, and then I say, oh, look, if it's sitting, if I, you know, I wouldn't expect to detect 10, I wouldn't expect to detect 1, let alone 10 signals from something that's so far inside, because the duty cycle to get in there would be minuscule. On the other hand, it's not close to the instability window, so it's not some kind of on-off cycle that's going on there. And so the explanation is that either in reality the window is different, it's stable, and then I need additional physics. Of course, there could also be unknown physics that leads to a very small saturation amplitude that's so small that it has no impact on either heating the system or spinning it down. This is also a possibility. So there are also constraints, and show here, you know, in X-ray on the saturation amplitudes that people have tried to look at this.
Yeah, please.
So you talk about mounting from neutron stars, right? So can there be dips in neutron star surface?
So, you know, when I say mountain, it's, you know, it's more of a word we say, but you know, you have to think of this. This really is a density perturbation throughout the crust, and we wanted to have a reasonably large. You know, if you think in spherical harmonics, you want to reach quite a large L because you know you can have high L's and very localized deformations, but then these are much higher order. When you look at the gravitational wave emission, they drop off with rather large powers of distance, so you wouldn't expect these. So it's essentially an L=2 mountain that we're thinking of, that can have, and to build a large quadrupole, you need these deformations also be fairly deep in the crust. So you know the surface is rather low density. You have some outer layers, an ocean and an atmosphere where you could have rather large deformations, but these don't allow for a very large quadrupole at all because the density is quite low. So yeah, mountain is kind of just a nice way to call it, but you know, you shouldn't really think of it as a mountain on the surface. It's more a big deformation of the star.
I wanted to ask about the supermassive white dwarfs. I mean, the white dwarfs that are expected to exceed the Chandra-Shekhar mass. Is it possible to detect continuous gravitational waves from this kind of sources? The detectors.
The person said these, but at what frequency will these be? Because my understanding was that they rotate significantly slower, right?
All I know is they have like pretty strong magnetic field. That's
Yeah, so they're strongly magnetic. I think they would be more, if I remember correctly, I mean, these, just because they're not as compact, do not rotate as fast, right? So it's, I know that I think, you know, usually white dwarfs are considered in the sort of LISA band with lower frequency. And so in fact, for LISA, these could be space-based detection. They could be a source of confusion noise for some distance.
LISA is in a way like dozens of years from now. That was the plan.
Yeah, I mean, I think it's been the Pathfinder was very successful, so it's been had a new LISA flight. So I think it's going to happen now. But, yeah.
So I don't see any questions from Zoom as well. So let's thank Bryn again. Sure. And for those of you who work here,